Hello students, so welcome back to the channel. So in this video we are going to be undergoing through the chemistry facilitation content. Now, like previously, we uploaded the pure mathematics together with applied mathematics facilitation content, and I was requested for a long time to also consider posting or uploading a facilitation video about chemistry. So this video is going to be mainly guiding you or presenting the final touches that you need to prepare for as you are preparing for your final examinations. So you simply get a notebook and then you take some of the summaries that I was able to compile for this video. So this video is presented by Mr. Olgembe Yusuf, and then you're advised to like the video and then share it to your colleague, provided is in Form 6 and offering advanced level chemistry. So let's get started. Now, the first point you're going to start with, you have been notified that presentation of work is very important according to what you know or to what you seem you have read. Now, in A level, especially in chemistry paper 1, we are testing for students' ability to present exactly what he or she has been asked. So when you're presenting your work, if at all they tell you to state, make sure that you just state what is required. Do not add any unnecessary information. If we tell you to explain, you explain. If we tell you to describe, you describe. You give a point together with the reason. So presentation of work is very important, especially when it comes to paper 1. If at all we tell you to state, you look at the mark allocation. If at all they are telling you to write the equation and the mark allocation is 1.5 a mark, you simply just write the equation. Do not add any other unnecessary statements, that will lead to a penalty. So I hope that is clear. Presentation of work is very, very important. Don't write too much. However much you know in any specific number, do not get tempted to give unnecessary details in case the question doesn't request for them. You can do that in paper 2, but make sure that for paper 1, you completely be very brief. The other point is that you must show good handwriting, especially when it comes to writing equations. Last year there were a lot of penalties for writing symbols in chemical equations written by different students in the country. If at all your handwriting is not that good enough and then you write any of these symbols improperly, you are not going to qualify for any mark concerning equations. So you're saying that avoid patterns and incomplete symbols in such equations. If you're writing sodium, this N, all symbols, the N must be well connected with all its 3 corners or its 2 corners. So if at all you're writing and leaving a space in between that letter, you don't qualify for a mark. So the whole equation is going to be wrong. Now if you look at here, when you're writing a symbol, you make sure that A, the other letter, which is the smaller letter, is halfway your letter which you have written. For example, this is the right formula for sodium. You write the capital letter which completes the line, and then the other letter which is small must be halfway that letter. So if you look at these ones, this one, the second one, the third one, the second one, and the first one are all going to be incorrect. So if you look at the third one, A is halfway our margin, which is our line. So this one qualifies to be correct. This one is incorrect because we tended to put a pattern between the two symbols. So sodium, there are 2 separate letters. You are not allowed to do any calligraphy. If at all it's a capital letter and a small letter, make sure that they are very separated. And the capital letter has all the corners, just like presented in the third step. And also the A must be halfway the margin or halfway the line. Now the other point of concern is that all the work must be in pen. This is not pencil. All the work must be in pen. except graphical drawings. Now I said for mathematics, I told you that all the work must be in pen, irrespective of graphs or drawings or diagrams. For mechanics, all the work must be in pen to prevent your work from fainting. Remember that your papers are not going to be marked at the same day. So pencils tend to faint. The longer the storage duration, the more your work starts to faint and you can't get any mark in case you have unclear work. So if at all you have confirmed that your points are properly presented, you can draw your graph using a pen to be on the safer side. Now when you go to calculations make sure that before you handle the given values in the question, you present the expressions where you are going to substitute those calculations or those values. By expressions, we mean that you present formulas. If you look at the marking procedure I stated here, the expression, the formula that you're going to provide, where you're going to substitute your values, is going to carry half a mark. And then the substitution into that formula is also going to carry you half a mark. Please make sure that you do not skip steps, especially with chemistry paper 1. The more steps you skip, the more you leave out marks. So for paper 1, sometimes the space is not enough. If at all you are provided with an insufficient space, you make sure that you divide that space into 2 using a straight line. And then you write here, and then later you also write here. But make sure for the case of paper 1, you do not skip any steps. Present all the mathematical data and all the mathematical calculations to prevent examiners having bargains on your paper. Now the final answer is going to carry also half a mark, and if you include units, you are also going to carry half a mark. So that's why if you look at most of the calculations in chemistry, you're going to have 2.5 marks, all summing up to this. Now remember that substitution may sometimes carry 1 mark. So you first start with your expression, then you substitute without skipping any steps, and then you simplify. Simplification is also going to carry half a mark, and then the final answer is going to carry half a mark. If you include units, you're also going to receive another half a mark. Now, if at all you do not include units, sometimes we deduct -1, and then by -1, you're not going to get this half mark for units, and you're also not going to get the final answer mark. So if at all the question is allocated 2.5 marks, you'll be getting 1.5. So I made a note here that make sure that you be brief, don't prevent unnecessary workings. So if at all for example, if at all you're having 2 squared divided by 4 squared, don't again first compute this to 4 and then divide by 16. Just find a way of utilizing up the space provided. So you skip some unnecessary workings, but make sure that you present the substitutions and also the simplification lines. They should be separate. So avoid over skipping steps. This is not mathematics. If you go to the next one, it's going to be converting units to standard known units. For example, for pressure and volume, this is very common with colligative properties. You make sure that before you start calculating, the given values are in their standard SI units. Pressure must be in its standard SI unit, which is Newton per meter squared. And then volume, we measure it mainly when you come to colligative properties, it's going to vary. But mainly make sure that it's in meters cubed. We gave you all those substitutions. You either multiply through by exponential -6 or you multiply through by exponential -3. This is very evident with colligative properties. And since most students are facing that challenge of failing to change the units to the standard known units or to the standard SI units, such questions keep coming back. I told you this earlier. So you make sure that you are very, very careful while presenting your data. Now, the other point of concern is going to be rating or balancing equations. Now we talked about this and we discussed this in details, and I showed you how to balance the different types of equations, both the ones involving alkali, the one for concentrated acids, the ones for dilute acids, and also the atomic equations. I taught all forms of balancing equations, so I don't expect any student on this platform to have issues concerning equation balancing. Now, when it comes to balancing equations, ensure that you don't leave any balancing numbers that may be presented in pencil. Some of you, when you're balancing, you tend to first use a pencil to indicate those digits, and then you forget to transfer them into pen. Now notice that if at all you leave your balancing in pencil, that balancing or that equation won't be considered to be balanced, because we tell you that each and every work that you present must be in blue ink or black ink, except for graphs, which we have also said that for the safety of your work, make sure that also you introduce your graphs in terms of pen. You have been looking at marking guides. All the marking guides that we write out and represent to you, the graphs and each and everything is in terms of pen. The pencil is not anywhere. So if at all you're a learner who is using a pencil to balance equations, make sure that immediately you do that. Then you transfer your pencil work into pen work. I hope that is clear. So the next point is going to be equilibrium reactions must be represented with reversible half arrows. Now, all chemical equilibrium reactions, remember that when you're starting that topic, we told you that chemical equilibria, characteristics of chemical equilibria, we told you that reactions are reversible. Another characteristic was all the experiments are carried out in a closed vessel. Because these reactions are reversible, products can easily turn to reactants, and reactants can easily turn to products. So whenever you're dealing with chemical equilibria, or you are dealing with industrial manufacture, because industrial manufacture of the different gases and acids is part of chemical equilibria. So you make sure that under such instances, you use partial arrows. In fact, when you're handling equilibria, because also ionic equilibria is going to be the same case. So in handling equilibrium topics, make sure that most of your equations, if at all you are not dealing with a strong acid in ionic equilibria, you make sure that most of your equations are separated or they have half arrows in between them, because those reactions are either way. So take note of that. Now, another thing is going to be about being careful with the spellings of the technical terms. Especially when it comes to electrochemistry, most students misinterpret this word, reciprocal of conductivity. Reciprocal, the word reciprocal is R-E-S-I-P-R-O. It's not I is not here, it's O. So reciprocal, when you're defining terms in electrochemistry, you make sure that you are very, very observant with the spellings that you're presenting. The common error that was very common in the previous years was the word reciprocal. Students, instead of O, they put here I. Avoid that. It's O, reciprocal. So use proper spellings for electrochemistry terms or for electrochemistry technical terms, especially with the definition of electrolytic conductivity. So take note on that. Now another point of concern is going to be about the bonds that we present when we're dealing with organic chemistry numbers. So with organic chemistry, we told you that the bonds must be very close to the elements. Very close to the elements. When you're drawing in shapes and structure, we told you that when you're drawing shapes and structure, the bonds must be touching or very close to the elements. So the right correct way is this one. You make sure that the bonds are either touching or very close without a noticeable distance between the different elements. So if you look at this, we're having a space here. That's why this one is wrong. And if you look at this one is wrong because we're having a 2 here and this bond is overshadowing it. So the best way, you either present it this way without crossing these two, or any three that may be present, or any number that may be present, or you present it this way by simply pairing up the carbon atoms. And when I do with the carbon atoms, for this one, the bonds must just enter, not inside, but they just enter the C, and the other bonds on the other side must be touching, or they must be very close, but you shouldn't leave a lot of space. For example, this is very wrong. These bonds must be touching. And when it comes to shapes and structure, drawing structures, you make sure that the bonds are drawn using a straight ruler and the bonds are touching the respective symbols or elements they are coming from or they are bonding to. Another one is going to be about molecular mass or the relative molecular mass. Molecular mass, relative molecular mass, and molecular mass, if used in calculation, we don't include units. Now, for this, let me make this very clear. If at all we use relative molecular mass, if at all you say relative, calculating for relative molecular mass, relative is a ratio. So as you say relative molecular mass, you don't include units. But if you say molecular mass, you can include units. Relative means ratio. So if at all you are handling relative molecular mass, do not include units of grams after calculation. But if at all you say molecular mass, then you are free to include units of grams. Another one is going to be getting quick tips of converting units, not to have unnecessary steps shown on the examination paper. Now, when you're in an exam, you make sure that at least you have a free answer sheet. Those answer sheets, after using it, it will be corrected by the invigilators. So you have a free answer sheet where you'll be presenting your unnecessary working. Don't present a lot of working showing how you are going to convert centimeters cubed to meters cubed during colligative properties. That is useless. If at all you know the shortcut, just have the shortcut. For centimeters cubed, we told you just multiply through by exponential -6. And if at all it has been provided in decimeters, we told you just multiply through by -3 to convert it to meters cubed. Do not present unnecessary working of trying to show how you are converting units. Do not do the mathematics in chemistry. Now the other point is going to be about avoiding repeating the question while answering questions. Now this is very common with paper 1 chemistry. We tell you to state the law. For example, we tell you to state Graham's law, and then most of you start saying Graham's law states that. That is unnecessary. So you simply say that the law states that, or it says that. Don't repeat the question. You are minimizing the space because we are going to provide you with 2 lines, especially for chemistry paper 1. And if you start by occupying the first line by repeating the question, that means that you are going to be left with a small space which may not complete your law, and then you are going to go down and then you start squeezing your handwriting, which in turn may end up straining the examiners. So if at all the examiner marking your paper is having high strains and it doesn't see what you have presented or what you have squeezed down here in the space which was not provided, you are most likely to lose those marks. So make sure that you're brief. If you're stating the law, you simply start by saying it states that, or the law states that. Do not repeat the question. Graham's law states like this. No, do not do that. Just say it states that. Say the observation when a solution of this is added to y. If you're setting the observation, just be direct. This color changes to this color. I told you when you're dealing with observations, we don't talk about chemical names of compounds. We talk about the initial color and then we talk about the final color. That's what is required. So this is going to take us to another point, that use only the space that has been provided, because it's going to be the most one to be considered, and it's because on the beginning of the paper is provided in the instructions. So they tell you to use the space provided. However, sometimes if you have made a mistake, for example, in chemistry paper 1, if I told this is your answer sheet, and you have answered question X and you have tended to make a mistake, and you occupied all the lines. So you simply close this line and then you go either up on your paper, and then you say if at all you want to repeat question 2 part A, you simply name it. The 2 part A, the law is going to state like this. But you only do this if at all you have made a mistake in the space that has been provided. And if you're crossing, you make sure that you cross with one line. That is enough to show the examiner that that work is omitted. And if at all you have made a mistake in that paper, don't, on that line or on that number, do not try to squeeze the right answer here. Just go above the paper and then you say that to part A, the law is going to stay like this. Or you just go below that very paper on the same page and then you say for question 4 part A, the right answer is supposed to be this. And then you write the answer, provided you put that number in a free space. But you make sure that it is labeled. I hope that is clear. So, however, any space in the paper provided can be used as long as your number is indicated, which I've just talked about. Now, the other issue is going to be about writing the benzene ring. When you're writing the benzene ring, when you're dealing with synthesis, I advise students to use this one. It's very okay to use this one or to use this one. Now, the main problem with this structure is that most of you, instead of making this circle to be very close to the points or to the turning points, you draw other components. For example, look at this structure. My circle, the space that has been left on either side is equal. This is what you call a Bayes structure. So if you tend to write such structure of benzene, you are not going to attain any mark. Your marks will be disqualified because that's not the structure of benzene. So if you're presenting benzene, you simply present it either in this format, which is very easy, or in this format, but you have to be careful about the relative distance that you leave on either side. So this is wrong simply because if you look at the distance sideways, it's not the same distance as the distance that was left upwards and downwards. So you make sure that when you're dealing with this one having a circle inside, you are very, very careful. Otherwise, if you don't want any issues, you make sure that you go with this structure. But also, if you're writing this structure, make sure that no bond is touching or crossing out of this hexagonal shape. So avoid that. Also on this one, make sure that the circle is a circle. Do not draw a C inside and then you call it benzene. You're going to be provided with enough time, don't be on a rush. So this one is wrong because the bonds are touching or they are passing through the hexagonal shape. So that does not qualify to be the structure of benzene. You make sure that the bonds, the pi bonds, are free inside the hexagonal shape. And that qualifies to be the most correct formula for benzene. Now the other question about that I got in the first facilitation I made was about either combining these two when you're dealing with the question. There's no, if you're writing synthesis, it's very okay to write these ones on the same synthesis. They all represent the same structure. But if you're doing mechanisms, we strongly recommend you use this one. Avoid the other one. The other one has led many students to lose marks on the examination in the examination centers. And the reason for that is because majority of your teachers do not now teach it to you the right way. So in mechanism, strictly use this structure. But in synthesis, you can use that structure, but make sure that the relative distance left on either side is quite the same. Don't make that circle to be favoring only one side or one length of the hexagonal shape. So I hope I've been very clear on the structure of benzene. Now the other point is about not every time we have a strong acid with a strong base, the pH is going to be 7. So here we are going to set, remember, to recognize the name of the salt that is being formed, whether it undergoes hydrolysis. Now mainly, if at all we have a strong acid and a strong base, mainly hydrolysis does not take place, but also it's very rare for us to set such questions. When you're examining hydrolysis, we are most likely to give you a strong base and a weak acid, or a weak acid and a strong base. So if you analyze such scenarios in any question, understand that it is going to be salt hydrolysis, which is very common in explanation questions in paper 2, but also does not miss in paper 1, section B. So if you have told you have not yet given the topic of hydrolysis enough time, you make sure that you use this remaining period to understand properly what salt hydrolysis mean and how it can come about. I made a full lesson about that on this channel, so make sure that you check it out. Now the other point of emphasis is that ensure that you use names instead of symbols or formulae while writing statements and special observations. When you're asking for observations, I told you, you simply state what you see. And when you're writing what you see, do not write any symbol or formula of any compound anywhere. If at all you're saying you're dealing with acidified potassium manganate and it's being added to an alkene, you simply say that the purple solution turned to a colorless solution. That's what it means by stating an observation. You don't state the name of the compounds anywhere. Observations, we don't expect you to see the names of the compounds. We are simply asking you for an observation, something that you can see with your eyes. So you simply rate the color changes which you can see by your eyes without mentioning any chemical name anywhere. And when it comes to trends, if at all we have given you a table, for example, group 2 table containing beryllium, lead, magnesium, calcium, we are going to provide you with symbols, but if at all you are stating and explaining your trend, we don't expect you to write symbols. If at all atomic radius is increasing from beryllium to calcium, you simply say you state the trend as atomic radius is generally increasing from beryllium, writing the full name, not the symbol. The moment you put symbols in the trend, you don't qualify to get a mark. The symbols are for the table. We expect you as a student to know the full names of those particular elements or compounds. So do not write symbols while explaining your work, unless when you are going to use inequality signs. For example, less than. For this case, if you're going to use inequality signs, it's very okay to use symbols. But if at all you're not going to use inequality signs, then make sure that the name of each element or compound is properly written on the spaces that have been provided to answer that particular question. Another one is going to be avoiding unnecessary ratings. And for this case, we are going to consider marking points only. I've already talked about that. Under answering questions that involve calculations, divide up your space using a straight line. Start with answering here, and then you answer here. Don't mix up your work. For example, you write here, and again you put commas, you write here, you write here. You simply, if you see the space will not be enough, you simply divide it using a straight ruler, and then you start by writing on your left hand side. If at all your left hand side gets filled, you transfer to the right hand side. Make your work organized for examiners not to have any issues or bargains about your paper. I hope that is clear. Now when it comes to ionic equilibrium, if at all you're having a strong acid plus a strong base, we call this one neutralization, and under such instances, we do not have salt hydrolysis taking place. And you're saying that if at all the concentration of protons or hydrogen ions is excess, then first get the number of moles. First get the number of moles from the mole ratio according to the equation. But mainly we looked at this when I was explaining ionic equilibrium. So I'm just giving you a review. Sometimes it's about the number of moles present and also the volume of something that has been provided. For example, we may have excess of a strong base and then we add less amounts of a strong acid. That means that we are going to have excess hydroxyl ions in that solution, and we expect pH to be above 7 because hydroxide ions or hydroxyl ions exhibit alkalinity. So make sure that you pay attention to the quantity of the substances given the question, especially moles. If at all you are given volume together with molarity, you make sure that you first calculate the number of moles of each element that you have been given. And by doing that, you're going to earn about 3 marks. Calculating for the number of moles provided when they have provided you with molarity together with volume, both for strong acid and for strong base. That carries a summation of 3 marks. And this is very common under investigating of complex ions as an application of ionic equilibrium. So just a simple review on ionic equilibria because it's one of the most commonly examined topics. So if you're having a strong base such as sodium hydroxide combining with a weak acid such as ethanoic acid, we expect salt hydrolysis to take place. And if you look here, we are going to form sodium ethanoate. That means that such a solution is going to undergo an ionic salt hydrolysis. So we expect you to have good knowledge about hydrolysis and how the pH of such a solution is going to be affected. When you're dealing with an ionic hydrolysis, I told you when we react to such an anion with water, it's going to accept a proton, leaving hydroxyl ions in solution. So we expect such solutions to be alkaline. You will be getting such questions under explanation questions in paper 2. Take time to fully understand ionic equilibrium. So Ka is the ionization constant of an acid. Kw is the ionic product of water, but ensure that the K is a capital letter and the A is a subscript. This means ionic constant of an acid. If it's Kb, it means ionic constant of a base. Then Kw means ionic product of water, which is the same as 1 exponential negative 14. And then Kh is going to represent the hydrolysis constant. We looked at all that under ionic chemistry. So you make sure that you review the topic of salt hydrolysis. So you're saying that when ammonium chloride is dissolved in water to make a solution, it is going to undergo salt hydrolysis. Why is it the case? If you look at ammonium chloride is a salt, and it's a salt made from a strong acid, which is hydrochloric acid, that provided these chloride ions. And then the ammonium molecule came from the ammonia solution. So if at all you get ammonia solution and then you react it with hydrochloric acid, you're going to form a salt of ammonium chloride. And since it's a salt made from a strong acid and a weak base, it is going to undergo cationic hydrolysis. So the ammonium ions will react with water donating protons. So they will donate protons to water to gain their stability. Now remember, this is going to be disqualified. I told you we don't have ammonium hydroxide in the laboratory. So if at all the ammonium molecule reacts with water, all conjugate acids donate protons to the water molecule. And then we end up with the ammonia molecule, which is stable. Then the protons that have been donated to water react with water to give us the hydroxonium ions. But not forgetting that I told you that most of the equilibria reactions must be with reversible arrows. So be it equilibria, chemical equilibria together with ionic equilibria involving weak acids and strong bases, or strong bases and weak acids. So we are going to avoid the ammonium hydroxide because I told you it does not exist in the laboratory. We shall strictly use ammonia. However, at UNEB, we are still considering the marking of ammonium hydroxide because it's a concept that has not been understood by majority of the teachers. But the most stable one is going to be the ammonia molecule. Avoid ammonium hydroxide because it's very unstable. So the others are going to be about calculating pH. When you're calculating for pH, you first have to find the value of the molar concentration of the hydrogen ions. And then pH is the negative logarithm to base 10 of the concentration that you have calculated. But remember, when you're dealing with these terms, when you're dealing with Ka, which is the ionization constant of an acid, Kb, which is the ionization constant of a base, and also the hydrolysis constant, remember that at equilibrium, both of these concentrations must be equal. And that is an assumption that you should write. You simply say that assumption at equilibrium, molar concentration of ammonia is equal to the molar concentration of hydroxonium ions. After writing that assumption, that's when you should square your bracket. I have emphasized that in the ionic chemistry series, so make sure that you review those videos. Ionic chemistry is a very common topic in terms of appearance in the examination halls or in the examination papers. So take note of that. Now the other point to note is that if at all we are adding very small, if at all the question is telling you that you are adding a very small volume, for example 1 centimeters cubed or 2 centimeters cubed, those are very small volumes. We are testing for a student's knowledge about buffer solutions. It's only when we are examining the student's knowledge about buffer solutions that we give such small volumes. So we expect you to say that when small amounts or when such a volume is being added to that particular solution the question is talking about, there is no change in pH, or pH is going to remain relatively constant, simply because such questions are testing for your knowledge of buffer solutions. So take note of that. And if you look at the question bank, those questions are repeating. They are coming over and over again. So if at all you are given small volumes, know that that is going to be test of knowledge of buffer solutions. So small volumes are added, assume that no change in total volume together with pH. So if you are calculating for pH, you do not add such volumes. That's a very common mistake. If at all the volume is less than 2 centimeters cubed, you don't consider any change in volume. And you also don't consider any change in pH when you're explaining questions. But when you're calculating, you don't add that volume by saying that, okay, those moles are in the total volume of whichever volume you have been with plus 1. That's very wrong. These are very small or minute volumes. You don't add the volumes, such volumes, onto the calculations of molarity or mole concept. And I've told you that we only examine such volumes when you're testing for a student's knowledge about buffer solutions. So when you approach such questions, make sure that you have a good explanation about buffer solutions, both the acidic buffers and the basic buffers, how each of them is brought about and how each of them performs when exposed to small amounts of an acid or a base. Now the other point is going to be about sketching a graph. Now, sketching graphs, I've explained these ones on my channel, the ionic chemistry graphs. You need to understand when the buffer solution is going to make. You need to understand when salt hydrolysis happens, where we have a steep graph rising or falling. And you need to understand where we are going to have excess of the component you're adding. So your graph must have the steep part to show salt hydrolysis, and then the graph which is rising gradually to show that some bit of buffer solution is being formed, and then your starting point should also be relative to 7, which is the neutral pH. You should know what is the relative pH of a weak acid. That's where your graph should start from. Or what is the relative pH of a weak base. That's where your pH should start from. Your sketching, so you should have, when you're sketching, you should ensure that your graph you label 7 because that's the neutral pH, and then you base from there to start your graph sketching. I've told you in these graphs of ionic chemistry, In this graphs of ionic chemistry, we test for a student's knowledge of buffer solution together with salt hydrolysis. So your graph, if at all you are dealing with a weak base and a strong acid, or a strong acid and a weak base, you make sure that you have regions for the steep part is for salt hydrolysis, and then the gradual part is for buffer solution being formed to resist change in pH. And we said before you start sketching, you make sure that 7 is labeled to ensure that your sketching is relatively either closer or slightly above 7, because most of the times you're going to be dealing with weak reagents. So if you don't have enough knowledge about sketching those graphs, check out the titration video I have in the Ionic Equilibria series together on this channel. So another point is that while sketching, the graph must not go beyond the pH of 14. Now notice that the maximum pH is 14, so don't oversketch for your graph to exceed that scale. The other point is correct directly related terms or concepts together while answering. For example, if I told you having pH directly relating to concentration of the hydrogen ions, this is a bit direct, but every one of you in senior 6, you should know that pH is the same as concentration of hydrogen ions. But pH is just the negative logarithm to base 10 of the concentration of the hydrogen ions, in case you have calculated them. Now, if you look at some of the hydrolysis, or some of the components that undergo hydrolysis, we are having aluminium, we are having chromium, we are having iron 3 ion, together sometimes with tin. So simply because of, remember that for salt hydrolysis to take place, the reason for it to take place is because the cations have small ionic radius or small ionic radii, and then they have high charge densities that enable them to distort the anions they're being attached to. So that's why we don't have nitrates of such cations. We don't have a nitrate of iron 3, we don't have a nitrate of chromium, and we don't have a nitrate of aluminium together with that of tin. So for that reason, but for tin, in direct situations we have it. But so for that reason, if at all these cations with high charge densities are combined with carbonates or hydrogen carbonates, especially in the laboratory, we shall see effervescence or bubbles of a colorless gas together with formation of the respective solid of that hydroxide. Remember that whenever salt hydrolysis takes place, we looked at this as a separate topic. I made that under Ionic Equilibria videos. If at all salt hydrolysis takes place with aluminium, it is going to distort this anion. So this carbonate is going to give us carbon dioxide gas. And then for it is going to react with the hydroxyl ions that come as a result of salt hydrolysis to give us an hydroxide. So aluminium hydroxide forms a white solid. If at all you are dealing with chromium, we are going to see a green precipitate together with the effervescence of a colorless gas. If at all you are dealing with iron 3, we are expecting to see a brown precipitate. Now notice that all those observations are due to formation of hydroxides of those particular elements that have high charge densities together with small ionic radii. And those are the reasons why polarization or salt hydrolysis takes place. So here we are telling that white precipitate due to hydrolysis of water molecules, and then bubbles of a colorless gas due to carbon dioxide. So carbon dioxide is as a result of this carbonate undergoing salt hydrolysis. And then the aluminium ions react with hydroxyl ions from the water molecule to give us a white precipitate of aluminium hydroxide. If it's chromium, we shall form chromium hydroxide, but chromium hydroxide is a green precipitate. Now these are the mainly examined, aluminium and chromium, and you need to know the equation for their hydrolysis. So in dealing with magnesium, if at all we are having magnesium ions in solution, magnesium ions in solution form a white precipitate due to the reaction with the carbonate. But for this case, we don't get bubbles of a colorless gas. Now remember that carbonates of group 2, they are insoluble in water. So if at all we get a carbonate and then react it with a test solution containing magnesium ions, we are going to see a white precipitate but without effervescence of any gas. So there we anticipate presence of the magnesium ion, but you look at this in details in your practical books. So the reason for that is because magnesium ion has the lowest polarizing power, and the reason for that is because it has a relatively lower charge density together with ionic charge, or it has a very large ionic radii which do not favor polarization to take place, and hence there will not be any hydrolysis taking place or accompanying such a reaction. Now for mechanisms, arrows must be touching and bonds must be connected. I've already talked about this. You make sure that your bonds are connected or they are very close to the elements you are taking them to. They are very close. This means that this element is very close. This arrow is very close to the symbol I'm taking it to. You make sure that you present them properly and appropriately, being very close to the particular elements. So we say that this one is wrong. The reason why this formula is wrong is because this bond here has to attach to the nitrogen. It's nitrogen that bonds with the phenyl ring, but it's not oxygen. So this was right, but what made this formula wrong is oxygen. It shows that this bond is attached to the oxygen, which is not right. The bonds from the phenyl ring have to attach to the nitrogen atom, not any other atom, not hydrogen, not oxygen. It's the nitrogen atoms that bond or that must be touching the bond from the phenyl group, as indicated on the first example. I hope you have noticed that. So most of you make this mistake when you're dealing with hydrazine. Make sure that you correct that. Alright, so these are going to be the hydrolysis equations that I talked about. I taught how to balance these types of equations. Now these equations are two. You can either write with non-hydrated aluminum ion, and then you get the usual hydroxide, or you can write an equation with hydrated aluminum ion, and then you get an hydroxide in this format. So there are two equations, and I taught you how to balance these equations when you're dealing with salt hydrolysis. Enter paper when you know how to balance them. These equations are going to be the same like that of chromium, though for chromium what is going to vary is going to be the observation. For chromium we get a green precipitate, but for aluminum we get a white precipitate or a white hydroxide. But the balancing is the same, and they are very commonly examined. Now the other component is going to be about chemical kinetics. When I give you equations about chemical kinetics, now remember that rate is equal to rate constant times the molar concentration of the reactants raised to their respective coefficients or appropriate powers. If at all you are dealing with calculations, you are not supposed to pick the coefficients that are present here in the question, because we are going to give you a table of values containing different rates of reaction at different temperature, also having different values. So to do that, you make sure that you simply write your equation containing unknown powers. Remember that these powers are going to be the orders of our reaction at the different rates of the chemical reaction. So you see, you don't pick the coefficients here, but you simply rate unknowns in case you're being asked for a formula, and this formula is going to carry either 1 mark or half a mark. I hope you're good with that. Don't pick the coefficients directly from the given information in the question. You simply raise to powers of unknowns, and then later use the data that will be provided in the table to make sure that you calculate for all these unknowns. You calculate for the order X, you also calculate for the order of reaction Y, and then you also calculate for the order of reaction Z. But mostly you're going to be dealing with two reactants, and then understand the formula and the definition for both rates together with the rate constant. You'll be good to go. So you're going to say that, therefore, that doesn't mean that the order x is going to be equal to a half, and also the order of y is going to be equal to 1, and also it doesn't mean that the order z is going to be equal to 2. I've told you that you have to calculate for those orders of reaction in respect to each and every reagent, x, y, z, or reactant. So you'll be given a table of values where we are going to give you a rate, and then you're going to give you an order, and then you compare two equations, or you use two equations to calculate for such orders of reaction. So the other point of concern is that avoiding abbreviation of words such as concentration to mean concentration. Now, in organic chemistry, the only short form that we allow is going to be conc. We don't have any other short form allowed to be written when you're writing your reagents or conditions. It's only conc when you're writing your synthesis or your mechanism. But if at all you are describing, make sure that each and every word is written in full. Most of you have a tendency of writing temperature by writing temp. Make sure that this stops in your notes. Do not apply it anywhere. You write full words. When you're describing or explaining or dealing with briefly explaining the different types of experiments. When you're dealing with experiments, when you're describing and when you're explaining, and it requires written form of data, make sure that you write everything in full. And I've told you that for organic chemistry, the only short form that we know is going to be conc. Nothing else about that. So the two statements are going to be different, both conc n and also concentration. Don't mistake the two. Now, if at all we look at commenting, sometimes you are not allowed to calculate, but you are told to comment about these rates of reaction or chemical kinetics. Now, to be brief, I have a lot to talk about. I'm just going to show you how you need to approach that. If at all you have calculated your order to be 2, so you simply say that as you double the rate, maybe also as as the concentration is doubled, also the rate of that chemical reaction is going to increase by 2 times. So you see, when you're commenting, you simply say that increases 2 times or increases by, so the word increases by 2 times is going to be wrong because it shows multiplication. By means multiplication. But and when you're calculating for those values, remember that you're going to be considering maybe experiment 1, rate of experiment 1 divided by experiment 2. So if you just say by, it means multiplication, and we are not multiplying. So if you're commenting, you simply say that increases 2 times as the concentration of the reagent X is doubled. So the rate increases 2 times, not increases by. By means multiplication. So you can't get a mark for that. This is chemical kinetics. So the full elaboration of that, in case you're required to make an answer and you're not required to do the calculation, you simply say that keeping the concentration of B constant in case the concentration of B doesn't change, and doubling the concentration of the other reagent after considering the two experiments. You say that the rate increases 2 times, but you avoid the word by. By means multiplication, and we are not multiplying. So you simply say that keeping the concentration of the other reagent constant and doubling this one, the rate is going to increase 2 times. Avoid the word by. That's a very, very common mistake done by majority of the students, and it has led to penalties in the examination halls. So the other point of concern is going to be in case the concentration vary and the rate remains constant, then you should obviously know that that's a zero order reaction. Now only temperature varies the value of the rate constant. We talked about this when I'm dealing with chemical equilibrium. It's only temperature which is the main factor. In fact, when you're asking you for factors that affect reaction, in chemistry, your first factor that you shouldn't forget must be temperature, because each and every experiment that we carry out, we carry it out at a specific temperature, and we do so that such that we get relatively constant results. So reaction where you are given the rate of reaction as the following. So these are further examples about commenting. So sometimes the question may tell you state what is going to happen to the rate if at all the concentration is doubled. So doubling means that you get the 2 and then you substitute it into the rate equation that has been given. And once you do so, after substituting the 2 into the rate equation where they say that the concentration is going to be doubled, then see what happens to the rate. If at all the rate varies, if at all the rate varies in any format, either increasing or decreasing, you simply comment based on the value that you have calculated. So here in words, you're going to say that the rate increases 11.31 times provided one of the reagents has been kept constant and the other one has been doubled. But this one to understand it fully, it is going to be from a graph work. I forgot to include it here, so we're going to skip it for the time being. But you can take notes and then you try to refer to the videos that I made about this in chemical kinetics. The reason why we over-examine chemical kinetics in paper 1 is because of the failure by majority of the students to understand this topic. So for that reason, we keep bringing it back. So when it comes to graphs, you must know the catalytic decomposition of hydrogen peroxide. When it comes to, remember that also we gave an experiment on this. You need to know both the experiment together with the description of the experiment and how you're supposed to treat different results. And sometimes in paper 1, we are going to provide you with a table of results and then we tell you to draw a graph and then identify the type or order of reaction. So iodination of propanone, we say that if at all we get a graph in this format or this format, iodination of propanone, we examine this in mocks, either Waukesha or Umuta, and we say that this one is always a zero order reaction. This one you should know it as a student before you enter for your paper. Now, if at all you are being provided with tables of results and then you plot your graph and then you get your graph to be in this format, we expect this to be a first order reaction. So we simply say that if at all the graph is going this side, it's going to have a negative gradient. So we simply say that since the graph we get a line of base fit, with a negative gradient, the reaction is a first order reaction in respect to whatever reagents that they have been describing in the question. So first order reactions, we get lines of base fit with either negative gradients or with positive gradients. So take note of that. But I already elaborated that in the chemical kinetics videos. We are just making final touches. So the way we are going to calculate for the slope is going to be equal to negative rate constant, the K means rate constant, then divided by 2.303. And the reason why I'm dividing by this is because I used log. If I use lean, then slope is just equal to negative K or negative rate constant without 2.303. Refer to chemical kinetics, I have explained that. So for instance, in this case, this graph was for lean against time. So for this case, slope is going to be equal to negative rate constant without dividing through by negative 2.303. As when you're that we do that when you're having our y-axis in terms of logarithm. But when you're having lean, you avoid that 2.303. Don't make that mistake. So when you're making the reason for why you identified your graph as a first order reaction, you simply say that it's a first order reaction. So reason for the first order reaction is the plot of whatever you're plotting on y-axis against time is a straight line with a negative or positive gradient. It can either be negative or positive, but you simply say that it's a straight line with a negative or positive gradient. If it's slanting, going downwards, that's a negative gradient. If it's slanting going upwards, it's also first order, but it is a positive gradient. So this is a negative gradient, this is a positive gradient. Positive gradients, slant going upwards. Negative gradients, slant going downwards. So you simply say that the graph represents a first order reaction in respect to that reagent that they're describing in the question. And it's because we have got a straight line with a negative or a positive gradient. So elementary types of reaction. Now remember that you need to understand what molecularity means and how you can differentiate it from mode of reaction. Molecularity, we told you that is the number of species that are engaging in a specific chemical reaction. And we also gave you the definition of the order of reaction, being the power to which the concentration term has been raised to in a rate equation at a given temperature. So you need to take note of that. So on that note, you can also consider reaction of hydrolysis of sucrose under chemical kinetics. Alright, this is some more data to consider about chemical kinetics. I'm not going to be explaining each of them, but at least I've talked enough about chemical kinetics. Molecularity is the number of chemical species engaging in a reaction, and then understand how to write the rate equation. So understand how to distinguish molecularity from orders of reaction and overall order of a reaction. We do not include catalysts in the rate equation, so take note of that. That's why they're having power 0, because we don't include catalysts or conditions in the rate equations. So that should be well noted. Now here I'm going to make a note that I already emphasized before in my organic chemistry revision videos. Most of the primary alkyl halides having 3 carbon atoms and below, when they react with alcoholic potassium hydroxide, we don't form alkenes. We form ethers, provided the chain is having 3 and below carbon atoms. Some of you have a tendency of trying to form alkenes from there, and UNEB examines that to test out this knowledge. We don't form alkenes, we form ethers, primary alkyl halides. If at all the carbon chain is 3 and below, we form ethers, we don't form alkenes. How can you form an alkene from that? You simply heat it with aqueous sodium hydroxide to get an alcohol, and then use concentrated sulfuric acid at 180 degrees Celsius to get a corresponding alkene, which you're looking for. But we can't get an alkene when you're using alcoholic potassium hydroxide. So take note of that. So you're saying that, but for secondary and then tertiary alkyl halides, for those ones we can easily form alkenes when you have used alcoholic potassium hydroxide. So this is a point of emphasis for attempting the paper. Please attempt only 6 questions in section B. Now it's like this. If at all you tend to attempt more than that, when you're dealing with paper 2, we only count the first 6 numbers. Now in section B, tell you to attempt 2 numbers. So if at all you have attempted 3, we are only going to consider the answer sheets that come first. We don't consider the number that you did well. We consider the numbers that came first. And then the numbers on the last page are going to be considered as rubric infringement. And for that reason, you are going to have less marks for not following instructions that have been provided on the paper. Your marks are going to be less. You have a penalty for that, because following instructions is also part of the examination. So you're highly advised to start with a number that you're well convinced with, or the number that you have been practicing for a very long period of time. If you're good at inorganic chemistry, start with inorganic chemistry. If you're good at organic chemistry, start with a number in organic chemistry. Give the first examiner who is going to mark your paper an impression that you know or understand the content. but don't put the number that you have performed poorly or that you have not completed on top. Arrange your answer sheets in order of the number that you are sure of to have done the best. If it's thermochemistry, put that number on top. Is it number 8? You put it on top. It's not about arranging the numbers in order. It's about arranging the numbers in order of what you did best, not in order from ascending. So make sure that you give the first examiner to mark your paper a good impression to others. I hope that has been clear. So for energetics or for thermochemistry, energy level diagrams must start with 0. I overemphasize this. When you're drawing energy level diagrams, remember I told you in thermochemistry, energy level diagrams are very different from Bonner cycles. They are very different. Energy level diagrams must show levels of energy with arrows going upwards and downwards. Bonner cycles, we only have arrows which may either be in form of a cycle. Arrows may not be straight, but arrows may be curved. That's why they are called Bonner cycles. So some teachers have misled students, telling them that Bonner cycles are the same as energy level diagrams. That's completely wrong. Energy level diagrams must show levels. I told that topic and I told you, when you're doing an energy level diagram, make sure that you present your data well on each and every level. And then understand that atomization energy is half the bond dissociation energy. That's a common concept to be examined by NEB, because that's where you make most mistakes from. And when you're starting your energy level diagram, after labeling your axis that is going to be potential energy in kilojoules per mole, make sure that you put here 0 at your starting point to show that your graph is starting from this place. So take note of that. So for energetics, energy level diagrams must start with 0, then positives and negatives. And then we talked about the bond dissociation energy, multiplying by the initial number of moles. Okay, for bond dissociation energy relationship, you need to understand the relationship between bond dissociation energy and then atomization energy. I've told you that atomization energy is equal to bond dissociation energy divided by 2, or atomization energy is half the bond dissociation energy. So take note of that. For the way we indicate those values on the energy level diagrams, I made the lesson on thermochemistry about that. So I'm not going to be over talking about that in this video, but make sure that you refer to it in case you are not good at energy level diagrams. But a key takeaway here is that energy level diagrams are not the same as Born-Haber cycles. They are two complete terms. When you ask you for an energy level diagram, you present an energy level diagram. When you ask you for a Born-Haber cycle, you present a Born-Haber cycle. Don't confuse the two components. So if you look at this, this is an example. This is an example showing you that when you're having bond dissociation energy, for you to get atomization energy, you have to have it. So I hope that is clear. These are examples of what I've just explained. Now also here, for you to get bond dissociation atomization energy for oxygen, you have to have the atomization energy, and that's why you're having the 2 down here. So this 3 is the coefficient of the oxygen atom, just like the way I elaborated it under the videos involving thermochemistry. Now the other category of terms, we can look at exothermic terms and also endothermic terms. If you look at electron affinity, it involves energy evolved. However, bond dissociation energy is the energy which is being absorbed to break a bond, so it does not qualify to be under exothermic reactions. Ionization energy is also the energy required. That's why it is falling under endothermic reactions. Now proceeding, there are some energetic terms that may involve either absorption or evolution of heat, or that may be either endothermic or exothermic. For instance, if at all you are defining enthalpy formation, for this one you are free to say that is going to be the enthalpy change, simply because enthalpy formation can either be endothermic or can be exothermic. So have a clear understanding of that. So same applies to enthalpy of solution. However, do not define hydration energy as enthalpy change. Hydration energy is going to be the energy involved. So its energy values must always carry a negative charge. So enthalpy of solution can either be positive or it can be negative, or it can be endothermic or it can be exothermic. Now remember that enthalpy of solution is affected by two factors. One is Let's energy, and then the other one is hydration energy. So make sure that you take a note on that. It's Let's energy that affect, it's Let's energy and hydration energy that affect enthalpy of solution. So if I try to ask you for factors affecting enthalpy of a solution, it's going to be Let's energy together with hydration energy. During enthalpy of solution, Let's energy must be positive. If you are calculating for enthalpy of solution, you make sure, because we tend to combine this question. First, we tell you to do an energy level diagram, and then you calculate for Let's energy. For that case, you are going to get Let's energy being negative. And then in part B, we tell you to calculate for enthalpy of solution for that particular compound. When you go to part B, you make sure that you change the value of Let's energy, you change the sign from negative to positive. Remember that I told you in solution we are dissolving, and when we are dissolving we are breaking bonds. So since we are breaking bonds, energy is required. So Let's energy tends to be positive. In part A, the reason why you've calculated and your answer is negative is because you are forming a compound. But in solution, we are dissolving that compound. So Let's energy must carry a positive charge. You change it from a negative, which you have got in part A, to a positive value. And then hydration energy, we have told you that hydration energy must always be negative, or it must always be exothermic. The other energy term that may either be endothermic or exothermic is Let's energy. Just like I've explained, we can define Let's energy in terms of formation of a compound, or we can define Let's energy in terms of dissolution of a compound or breaking of a bond from the respective ions. So if at all we are forming a compound, Let's energy is going to be the energy involved when gaseous ions react to form 1 mole of a compound. When you are forming, we evolve energy, but when you are breaking, we absorb energy. So take note on the definition of Let's energy. So when you go to Uace's law, we are saying that for Uace's law, Bohr-Haber cycle must be with balanced equations and also correct state of symbols. Now in thermochemistry, before we mark your script, what you're going to consider is whether you have presented the right states on the different presentations that you have made on the paper. So the first thing to consider is whether the equation is balanced. After ensuring that the main equation is balanced, you have to make sure that each and everything is present in its standard state. Without states, you don't consider to get any mark. So for thermochemistry, we are a bit very strict. You make sure that states are well stated and symbols are well written, and the main equation is well balanced. So that being mentioned, let's look at the components. In case you're handling an inorganic equation, what are the components for you to get all the marks or the 1.5 mark on any given equation? So an equation, first it must have correct chemical symbols of the respective elements. We have already talked about this. And secondly, so this is a half. And secondly, it must be correctly balanced. So these two, correctly balanced and carrying the right symbols well written, is going to carry half a mark. And then states, if at all you give all the states or you mention all the states on the respective elements or the respective compounds, you're also going to earn another half a mark. And then arrows. If at all you have indicated a proper arrow, that the arrow is coming from the reactants to the products, or in case you're dealing with equilibria and you have indicated that it's going to be a reversible arrow, this is also going to carry half a mark, and this is going to sum up to 1.5 mark. So avoid use of wrong arrows. Know when to use reversible arrows and know when to use full arrows. For inorganic equations, if you missed it, you will get only 1 mark on that particular equation. So take note of that. The other point of concern is going to be to never use word partially filled while commenting on the stability of the different subenergy levels. Now I told you to avoid the word orbitals and then use subenergy levels. If you have been on this channel long enough, I told you to avoid orbitals and strictly use subenergy levels for the safety of your marking. Now here we say that we are not going to be using this word partially, because partially, if you look at partially, even something that is half filled is also considered to be partially. Even if you're having 1 electron in the subenergy level, we're also considering this one as partially filled subenergy level. So we should avoid this word at all costs. I over-mentioned it and I over-emphasized it in my previous facilitation. If at all, we only mention halfly filled and then fully filled energy levels. So if at all you are not having a partially filled or a fully filled energy level, you simply state the number of electrons that are present in that sub-energy level. If at all you're having 4 electrons, you say that since for example, halfly filled and then fully filled, we say that for them they are thermodynamically stable. So they will affect the magnitude of ionization energy together with the electron affinity. But for those ones that are not partially filled or fully filled, then you are supposed to mention the number of electrons that are present in that sub-energy level to make it thermodynamically unstable. But do not use the word partially. So you may say that whereas for calcium, maybe for calcium or for phosphorus, it has only 4 electrons in the p sub-energy level, making it thermodynamically unstable. And then you proceed with your explanation. But do not use the word partially anywhere. This is very wrong. And it's a very common mistake on most of the schools, because most teachers find themselves marking you. So avoid that when you're approaching or when you're dealing with periodicity explanations. Now another point of concern is going to come from stating trends or explaining trends. Now we give you a table containing the names of the elements. We give you a table containing the names of the elements or the symbols of the elements. Remember, I told you when you're setting the trend or explaining, you should not write symbols, or you should not use symbols in your answering. You make sure that each and every element or compound, you give it its full name. Do not use symbols. And I say that you're only allowed to use symbols if at all you are going to use inequality signs of less than. So if at all they are provided with the elements and you are seeing them, because they are going to be about 3 to 4 or 3 to 5, you make sure that you mention them, but avoid words like across period or down the group. You simply mention that from beryllium to calcium, atomic radius is doing this, or from this to that, atomic radius is doing this, or atomic radius is increasing from this to that. Now if at all you're having only 3 elements, you make sure that you mention all of their names. But if you're having more than 3, then you can say from the first one to the last one. But if you're having only 3 components in the table, then you mention all their names. Maybe from sodium to aluminium, from sodium to magnesium, then to aluminium, when you're having a table containing 3 components. But if at all you're having more than 3, then you say that atomic radius or ionization energy is increasing from the first one to the last one. but avoid words like across the period or down the group, because most of the cases we do not provide all the elements of that period or the group. So if at all we have not provided all the elements or compounds of that element or group, that means that this word that you're going to be using is going to make your explanation or your trend to be incorrect. And that's the strictness of chemistry paper 1. You have to be very, very observant. You only mention and talk about the elements that are being talked about in that particular group or in that particular period that are being provided in the examination paper. Do not generalize and set down the group. We have not provided or we do not provide all the elements in that group or the elements in that period. And when you're starting to explain, remember I told you when they're telling you to say the trend, you simply say the trend. Don't add anything. If at all the question is just telling you to explain, you start by stating the trend. After stating the trend, you put a full stop and then you start explaining. Ionization energy is increasing from this to that because do not say that ionization energy is decreasing down the group, because we have said that avoid words like down the group and then across the period. You simply mention what you are seeing on the table. If it's ionization energy, you say that is increasing from magnesium to aluminium. You mention what you are seeing in the table that has been given in the question. So avoid generalizing by saying across the group or down the group. Completely avoid that. The next thing is going to be if at all the value is given are negatives or they are mixed, negatives and positives, then correct trend should be okay. This one is a bit logical, but I think I'll explain it to my students in person. But if at all you have mixed values containing negative and positive values, that means that those ones are energy changes. Those ones are energy changes. The one which is more negative evolves more energy, and the one which is more positive evolves less energy or even takes in energy. And this is very common when it comes to electron affinity. But when explaining electron affinity, remember that the definition is in terms of energy evolved. The definition is in terms of energy evolved. So if at all you see that one of them is more negative, that means that that particular element or that particular compound gives off more energy. You explain in terms of the definition. If at all you're dealing with electron affinity values, you explain in terms of electron affinity. I hope that is clear. So if it's negative, you say that this value is going to be more negative. The value is more negative because it gives off more energy, since adding the electron is going to give off more energy. And if it's more positive, that means that we expect that sub-energy level to be thermodynamically stable. And we say that energy levels that are thermodynamically stable are either half-filled or they are fully filled. So for that reason, adding an electron will require energy instead. That's why such values are positive. So negative and positive values given in the table show evolution or absorption of energy, which I'm talking about here, exothermic or endothermic. Now going to electrochemistry, we're going to say that all electrode potential values must be reduction potential values. Now this applies to calculations. Before you tackle any calculation, you make sure that all the half-cell equations you're having are in terms of reduction potentials. And we say that EMF of the cell is equal to the EMF of the right-hand electrode minus EMF of the left-hand electrode. So you should note that. So some of the other points to note under electrochemistry is that before starting your calculations, in case you don't have a reduction potential of cell equation, then you are supposed to reverse those equations. And remember, after reversing, the sign on the values must also change. If it has been positive, it changes to a negative. If it has been negative, it changes to a positive. And when you're writing the electrochemical Soul equation, the left-hand side must be this side and it must be oxidation, stoked with the electron donor. The anode is going to be a reducing agent. I overemphasize this under electrochemistry videos, so I'm not going to say much on that because according to the items I see most of you giving, it shows that you're very good at that. But make sure that before calculations, all your Soul equations are in terms of reduction potentials. I hope that is clear. Now for diagonal relationships, we are going to start with the first elements according to the groups. Diagonal relationships, you are going to be provided with a periodic table. So you see that lithium will be paired with magnesium, beryllium will be paired with aluminium. You start with the one which has the low atomic number to the one with the high atomic number. Don't say magnesium and lithium. No. You start, it's a diagonal relationship from top to bottom. So you mention them that way. Lithium and magnesium, beryllium and aluminium. It's a diagonal relationship. I hope that is clear. Boron and silicon. You must know all the three pairs that participate in diagonal relationship. Then the reasons for why pairs engage in diagonal relationships, I told you that is periodicity. You talk about periodicity characteristics. One being smallest atomic radius, then the other being relatively them having quite similar atomic radius, having high electronegativity, electropositivity, similar electropositivity, similar electron affinity, similar ionization energy. When they talk about reasons or when they ask you why, you simply state periodicity terms that we looked at. Electron affinity, atomic radius, electrode potential, all the periodicity terms that we looked at are the ones that you mention under the reasons why a certain pair engage in diagonal relationships. Now there are two. Sometimes we may either tell you, sometimes it may be atoms or you may state ions. Say the ions that engage in diagonal relationship. Now here, when you're setting properties, I don't know whether you understand me here properly. When you're setting properties, I told you that properties means reactions. If at all you have given me a pair of lithium and magnesium in part A, and then I ask you for properties or for ways in which such a pair shows diagonal relationship, I'm asking you for reactions observed in those two elements. So you can start by saying that both of them form ions, both of them form ions with high charge density. Both of them form ions with polarizing power, with high polarizing power. Now here you are seeing that we are talking about charge density, polarization power, and ionic radius. These ones are under periodicity values. But this one comes in case you are looking for more reasons which are not attached to their atoms. Because when lithium and magnesium, after setting them in part A, the examiner is considering them as atoms or elements. So whatever you're talking about must be affecting atoms, such as smallest atomic radius, such as electronegativity, electron affinity, or ionization energy. All those factors affect atoms. But if at all you are looking for more reasons, and the reasons are not affecting atoms, then you need to say that both lithium and magnesium form ions which have high charge density. Both lithium and magnesium, or both beryllium and aluminium, form ions with high polarizing power, or with quite the same polarizing power. I hope I've been good. Don't say that both of them have high charge density. That's wrong because you have stated them as atoms in part A. Atoms cannot have a high charge density. I hope you are getting me. So first, they have to be ions for them to have a charge density and polarization power. So you start by saying both of those two elements in that pair form, yes, I underline this word, both of them form ions with high charge density, high polarization power, and form ions with smallest ionic radius. I hope you have got the difference. So proceeding, we are saying that for reactions or for properties involving diagonal relationships, some of the properties that you're going to mention are going to be for atoms or elements, like the way you mentioned it in part A. And other reactions or other properties that we'll be talking about, they are going to be for compounds or they are going to be for ions. So under such instances, you simply say that both, let me say both lithium and magnesium form these compounds which undergo this reaction. For example, they both form hydroxides which are amphoteric. We need to see that word form, because in part A you just gave us atoms or elements. So if at all you're talking about a property or a reaction involving compounds or ions, you have to tell us that both of those elements are going to form, that word must be there, both of them form compounds or they form ions that engage in such and such a reaction. I hope that is clear. So the more electronegative one element is, the more positive is electrode potential. This is still an emphasis under electrochemistry. Now remember I told you that when you're dealing with organic synthesis, ensure you have enough options for forming the different types of compounds, either extension of a chain or elimination of carbon atoms from a chain. Some of the most common ways that you're having during synthesis for expansion of chains, one of them is going to be Guignard's reagent. Ensure that you mastered it properly and how to use each and every specified reagent. Now on this, I told you to avoid boxed arrows. Make sure that all your arrows are straight. Either, if you're going to the next line, you make it diagonal. Conditions must be up the arrow, conditions must be down the arrow, and then reagents must be on top of the arrow. So take note of that. So expansion of chain, you either use Guignard's reagent or you use potassium cyanide, alcoholic potassium cyanide, and then you warm. If at all you have forgotten to warm, you may say alternatively that you heat. They mean the same things. But mainly for alcoholic potassium cyanide, you may say warm. It's the most correct answer. But also student who has said heat also qualifies to be marked. So on this, you also take note of that. Do not use boxed arrows. Your arrow must be straight, either diagonal or horizontal or vertical, but it shouldn't be straight. If you're writing conditions, like for this one, these conditions would have been this side, and then these reagents would have been on the top side, and then the condition, which is the warming, would have been on the other side of the arrow. So take note of that. So another point of concern is going to be having 3 different alternatives of reducing carbon chain. You need to understand soda lime, how we are going to use soda lime in reducing carbon chain, and also how we use ozonolysis in reducing carbon chain. There are very many different ways of reducing carbon chain. Also, amalgamated zinc can do that. But make sure that you have 3 different options in either extending or decreasing the carbon chain of whatever product or whatever compound that you're dealing with. The other thing is going to be to feel free to change the ring to bonds whenever you're dealing with the benzene ring, especially before mechanisms. For mechanisms, we say that you're going to be using this structure of a benzene, having pi bonds inside it. But if at all you're dealing with synthesis, it's very okay for you to switch from this structure of benzene to another structure containing a circle inside. I told you that if at all you're doing this circle, you make sure that you do it properly. For this circle to be evenly positioned. Do not draw the other ones that have unrecommended earlier in this video, where you draw a bigger structure then you draw a small circle. This is no longer benzene, so you don't qualify for a mark. But the most appropriate one is this structure, especially when you're dealing with mechanisms. This one will not lead to penalties. But if you're dealing with synthesis, it's very okay to interchange between this structure and this one. there's no penalty in that. And then while dealing with the mechanisms, when you're breaking off the bond, the positive charge must be on the carbon. Most of you have a tendency of putting it in the middle. The positive charge must be positioned at the corner, showing that it is on this carbon which lost a bond. And when you're breaking this bond of hydrogen, you make sure that either the arrow has just entered, its tip has just entered this benzene ring, or you simply put the arrow just inside. The arrow head must just be inside, or you make sure that its tip enters this benzene structure. That's how we break that bond. So take note of that. So another point of concern is that if at all you have used a ring in mechanisms, make sure that the other 5 carbon atoms are covered up by the half of the C or half of the circle that you make. But I've discouraged for this, if you're on this platform, I've discouraged the use of the ring, the benzene structure with the ring inside when you're dealing with mechanisms. Now, if at all you're dealing with mechanisms, it's very wrong to change from the other structure having pi bonds inside it again to rings over the different steps. So I say that it's wrong to change between a ring and bonds when you're dealing with the structure of benzene during the course of the mechanism. For mechanism, you deal with one structure, but for synthesis, it's very okay to change between bonds to the ring. I hope that is clear. For mechanism, you must use one structure because they all represent different pathways when you're handling mechanisms. So with that, this is what I mean. If at all you are in the course of the mechanism, you are not allowed to shift from this structure to that structure. This is completely wrong. You are not going to qualify for any mark. Then the other point of concern is that revise the trends and then the reasons for the solubility of hydroxides together with sulfates of group 2 elements. Remember, we have took long without setting this question. You need to understand how does the solubility of the hydroxides vary down the group of group 2 elements, and then how does the solubility of sulfates vary down the group of group 2 elements. Now, don't get me wrong, I'm not saying that it's going to come, but make sure that you have a good understanding of that. Understand the solubility of both the hydroxides together with the sulfates of group 2 elements. Alright, now this is the first facilitation that I had with you before. So for this I'm not going to emphasize much because I've already mentioned all of this. So if at all you didn't receive a copy of that facilitation, which was facilitation number 1, you may simply just go through making notes of what has been summarized in this session or what was summarized in that session. So for this, I'm not going to explain much because I've already explained everything in details. So just be giving you 1 minute, or you pause the video and then you try to take down the information that was noted. Alright students, so this brings us to the end of our facilitation session. So after this video, since we have provided the facilitation for both mathematics and for chemistry, then I expect you to get only distinctions, A's and B's, nothing else. So if you have found this beneficial, you make sure that you forward it to your friend for the support or for the academic support, so that you all excel as a team. Shout out to my students. Ensure that you get enough A's in this year. There's nothing that hasn't been touched on, especially if you have been long enough on this channel. If you're having your Form 5 friends, you make sure that you refer them to this channel as soon as possible for your school to get better results. So meet in the next session. I remain Mr. Olgembesu.